So let me make that a bit more concrete. So suppose I have a distribution whose IMAP looks like this. So this is a distribution over 5 variables. And this graph here on the left represents conditional dependence relationships. So say variables 2 and 1 are independent given 3, 4, and 5, so on and so forth. There's a bunch of independence relationships embedded in this graph. I can compute the sparsity pattern of a map that will take samples from this distribution and transform them to a Gaussian. And I can compute that sparsity pattern before I actually compute the map. That's the key idea. And I can compute the sparsity pattern essentially by performing a sequence of graph operations that involves sort of peeling off nodes and then marrying their children. So peel off 5, it's called moralizing the graph. Get everyone married off. So peel off 5, 4 and 3 are already married. Peel off 4, 3 and 3 is already married. The children are already married. Peel off 3. Okay, now I need to draw a new edge between 1 and 2. That gives me a sequence of graphs, and this sequence of graphs will tell me the sparsity pattern of the inverse transport. And the sparsity pattern is as follows. So basically the fifth component, rather than be a function of all 5 variables, is a function of only 3 variables. The fourth component is a function of only 2 variables, so on and so forth. So this sparsity, of course, depends on the labeling that I put here. But this is very much, if you're a numerical algebra person, like computing the sparse Cholesky factor of a sparse matrix. So you begin with a sparse matrix. Think of that in the Gaussian case as your precision. I want to compute a sparse Cholesky factor of that precision. So I'm going to find the appropriate permutations and pivoting, things like that, to preserve as much sparsity as possible in the precision. And that's basically trying to find a good ordering for this graph. Okay. But the upshot is that given a sparsity pattern for pi, my map S is itself going to be sparse. And that's going to be good news from the perspective of learning this map, because this map, for instance, rather than being a function of n variables, this component might be a function of only 2 variables or 3 variables. So there's some low dimensionality that's going to come in how we describe the distribution, and and that's going to be very important when we try to learn this distribution from a finite number of samples, because we essentially need to find 2-dimensional functions rather than n-dimensional functions, depending on the sparsity pattern. Okay, so 2 more ingredients, and then we'll put everything together. The fourth ingredient says, okay, what is useful about this triangular structure? So this triangular structure, other than the fact that we can relate it to sparsity, is actually going to let us do things like simulate from conditionals and conditionals of interest. So now let's begin, and I'll describe that as follows. So suppose I have some map S that takes samples from pi and pushes them forward to eta, and eta is my standard Gaussian. And I'm just going to use z to denote the samples from pi and x to denote the random variable distributed according to eta. And let's consider, so S is some triangular map. But now let me consider a triangular map that is not the whole of S, but what happens when you chop the head off of S. So I'm going to chop the sort of upper triangular part of S. I'm going to remove it. I'm going to condition on the variables that correspond to that head. And I want to basically draw samples from the rest. So I'm going to basically just, let's say I construct the map that's like this. It takes the components of S rather than, it chops off components 1 through k, keeps components k plus 1 through n, and fixes the first k inputs to xi, whatever xi is. So viewed as a function of the z's, the remaining z's, zk plus 1 through n, this is a triangular map right here. Essentially, because these are, think of these as constants, and now these is kind of the active variables, zk plus 1 through n, so this is a triangular map in that. Now this map, this is a conditional map, pushes forward a particular conditional of pi to the reference marginal. So this map, by construction, actually pushes forward z, k plus 1 through n, conditioned on the first kz's to the reference marginal. And what that means is then if I want to sample from this conditional, what do? I draw a sample from the reference marginal. So I pick a Gaussian, fix that Gaussian, and then solve for zk plus 1. Fix that, solve for zk plus 2, so on and so forth. So essentially back substitution. So this lets me basically do conditional simulation by just doing a bunch of one-dimensional root findings. But essentially solving this triangular system like this. So I can sample from the conditional because of the particular ordering that I chose in constructing this triangular map. So if I want to condition variables that are further down on variables that are further up, that becomes an easy operation. Okay, so the final ingredient. I talked about the existence of these maps. We talked about their sparsity properties. We talked about how to use them for conditional simulation. But how do you construct them in the first place? So this is an important ingredient. There's two types of calculations that we're going to have to consider in the scheme. One is, what if I have an unnormalized density that I know in closed form? So I don't need to know its normalizing constant, but suppose I actually know the density pi. That's going to show up at a certain step of our filtering algorithm. And I want to find a map T that basically describes pi as much as possible. So one way to pose that is by solving an optimization problem. And again, if you come from machine learning, this looks a lot like a variational Bayesian method, where this is the KL divergence between the push forward of eta under T and pi. And I want to make these as close together as possible. I want to drive that divergence to 0, which will say that these distributions are the same. I can rewrite that as follows, and I'm going to do this minimization over some set of monotone triangular maps. And it turns out this problem is actually quite tractable, because it involves expectation with respect to the reference. It's going to use evaluations of pi and its gradients, and this is a pretty, straightforward problem to solve. And just to kind of give you an example of it, suppose my pi is this target here, and suppose the reference is the standard Gaussian here, and I put them on the same set of axes. I can solve this optimization problem, and what I'm going to show you here is basically samples from the map at each step of the optimization problem. So basically, I'm just actually doing a quasi-Newton method, BFGS, and these 4 frames of the cartoon are literally the 4 steps of BFGS. Beginning with an identity map, which is a bad guess for the map because the target is over here in the tail. Solve this problem using gradient-based optimization, and the particles are pushed to the region of interest. Now, I put this cartoon here kind of for a reason, because this actually says this is something you would not be able to do with importance sampling. If I began with this sort of set of samples as samples from a biasing distribution and tried to weigh them according to the target, it's kind of hopeless. This sample over here would get all the weight. These samples would essentially have no weight. And this sample that has all the weight would be a terrible representative of the whole distribution. On the other hand, this encapsulates this notion of moving particles into the region of interest. And how do you move the particles into the region of interest? Well, by finding the transformation T that does that. And how do you find the transformation T? By solving an optimization problem over the parameters of the transformation. So the key thing here is that we're using gradient-based optimization. You're able to look at the gradients of pi, or saying the bulk of the distribution's over here, the gradient is very strong and pulls you over, and it does the job. Okay. You can also sort of intuit, this is the KL divergence objective function that's kind of been rewritten. Essentially, so this is trying to make this small. So I could say I'm trying to make log pi composed with T large. So that says let T move the samples to where log pi is large. So let T move the samples towards the mode. That's good. But on the other hand, I don't want all the samples to go to the mode, because that wouldn't be a good representative distribution. And that's what this penalty term here is. Essentially says, don't make T too flat. If T becomes very flat, then all the samples go to the same place, and I don't want that. So there's a balance between these two things. It's not like we have to prescribe it. This just comes out of the KL divergence. Okay. So that's one way of constructing maps, if I know the density up to a normalizing constant. The other thing that we're going to have to do, because remember, I'm trying to do this in the context of I only have samples from the forecast, is construct a map from samples. And to do that, I'm going to consider, okay, suppose I have suppose I now have samples from pi, and I want to construct a map. I'm going to solve a slightly different KL divergence minimization problem. Notice what essentially here I've flipped things around, so now pi is on the left. And this optimization problem actually has really nice properties. So as long as for Gaussian eta, this problem is going to be convex, and it's actually going to be separable across dimensions, regardless of the form of pi. Because here we're representing pi by samples. So essentially there's an expectation over pi, and that gets sort of rewritten as a summation over the samples that I have. And the objective involves this quadratic log eta, and that involves the Jacobian determinant of the map. So this you can verify as a convex objective, and this is basically for each component of the map sk. I solve this, and we're done. Okay. So all these ingredients. So this is a long excursion. How does this go back into the filtering algorithm? So the idea is as follows. So we're going to think of ENKF type approaches, but now we're going to use all these tools that I described in the past 20 minutes. And we're going to say, we start with a forecast ensemble that we get by running our samples through the dynamics. And we'd like to transform the forecast ensemble into approximate samples from the filtering distribution via the couplings. And then, of course, we'll evolve. Then we'll take the samples from the analysis ensemble, then evolve the dynamics again. And we'll just sort of repeat. So the evolution phase is simple. They just apply the dynamics. The key action really happens in the assimilation phase. So what happens in the assimilation phase? I'll break that into a couple steps. First thing we're going to do is, given samples from the forecast distribution, we're going to approximate a description. We're going to take those samples and use them to to come up with a description of that forecast distribution by projecting the samples onto some manifold of sparse non-Gaussian Markov random fields. So we're going to assume some local probabilistic interactions. We're going to try to capture the non-Gaussianity and capture the prior, if you will, that forecast distribution in some structured class of sparse GMRFs, non-Gaussian GMRFs. And then we're going to start to simulate the observations one by one. And with each observation that we simulate, we're going to propagate that information across the state. So to kind of abstract this problem away, if you're a Bayesian inference person, the core of this problem is that you essentially have samples from the prior. You don't know the prior density, you just have samples from the prior. And then you have a likelihood that you can evaluate in closed form. And given those two things, you'd like to actually now generate samples from the posterior. Okay? That's the essence of the problem, boiled down. So how does this work? So I have a bunch of samples, and I'm going to project the forecast onto a manifold of sparse MRFs. So what does this mean? So what sparse MRFs do I pick? Well, I'm just going to pick a Markov structure. And this is maybe kind of a relatively arbitrary thing in an algorithm right now, but you could think of this as akin to localization or any kind of other regularization. I'm just going to pick a Markov structure. The Markov structure, maybe it'll look like this. Everyone interacts with its neighbors. That Markov structure is going to tell me a space of maps that I can consider, because I can map directly from the Markov structure to the sparsity pattern of triangular maps. Now, given samples from the forecast, I'm going to use those samples to learn a map. And in learning a map, essentially, I'm learning an approximation of the forecast distribution in this class of distributions that have this particular Markov structure. Okay? So I applied those ingredients before. I learned the inverse map from samples. That's a convex optimization problem. And that's the first step. So essentially now I've described the prior, given samples, all the information I have, in some restricted class. And now let me say, okay, now I want to start assimilating the observations. So I have described the prior, and I'm going to sort of throw away the conditioning on the previous y, so I'll just call that pi of z. Now, the posterior can be factored in a certain way. So for instance, let's just consider that I'm going to assimilate one observation at a time. You can generalize this to multiple observations, but let's just say I have this prior, maybe all these observations are, all the states are on a ring, and then I observe one of them, which is, say, this red observation that's hanging off of this node. So I'm going to call this node up here Z1. Now, I want to condition, and this red thing up here is Y. So I want to condition all of the Z's on this Y, but I can factor this because of this Markov structure is pi of Z1 given Y, and then pi of Z not 1 condition on Z1. So essentially I just factor this into 2. And now I essentially have two steps. The first thing is conditioning on the Y. So I have this node Z1 that I had its prior, I had its marginal, and now I've observed something about it. So I'm going to be able to update from the marginal prior to the marginal posterior of that node. So I need to simulate from Z1 given Y. So how to do that? Well, I need to know the target density, Z1 given Y, and then I'm going to use the notion of constructing maps from unnormalized targets. So what is the target density? Well, I have the likelihood, pi of Y given Z1, and then I have what is the prior on Z1? Well, the prior is something that I can construct from the map that I learned, construct from that S. So this is essentially the prior on Z1. So this is a one-dimensional inference problem, and I need to generate samples from this posterior. And I can do that with one-dimensional maps. Okay? Pretty straightforward. Now, so that one-dimensional map is going to be T1, and then as far as node Z1 is concerned, I'm done. The composition of S1 and T1 is going to take forecast samples of Z1 and transform them to analysis samples of Z1. But now I need to deal with the rest of the state, Z not 1, so Z1 through N. Essentially, you can think of this as propagating what you've learned about node 1, propagating it to the rest of the state. So this is the first node. I've conditioned it on the data, so now I have essentially posterior samples. I have samples from this marginal of the posterior, and I need to propagate that information out. But that is just conditional sampling. Because I already said I have this joint distribution in the prior, and it factors in a certain way. And if I condition on the first node, say if Z1 is the very top of my triangular map, and I want to draw samples from the rest, essentially I fix this C according to Z1, and I sample from the rest. So basically I use the conditional simulation strategy to draw samples from Z not 1 given Z1. Okay? And I push that information around. And I could repeat that for the next observation. There's some simplifications in S because, of course, S is sparse, and you could sort of make this more complicated and assimilate multiple observations all at once. But in essence, this is what's happening. So if you put this all together, you have constructed our desired object, which is a transformation from the forecast ensemble to the analysis ensemble, where this S is the map that I used to represent the forecast. The T1 represented the kind of reference to posterior marginal for Z1. And then this thing here, which is the conditional map with T1 embedded in it, does the rest of the propagation. So this composition here, curly T, is what transforms the forecast ensemble to the analysis ensemble. Now I claim that if all these were restricted to be linear, then this kind of essentially reduces to something like an ENKF, but with not sort of tape assumptions on the structure of the covariance, assumptions on the structure of the precision matrix. But the key idea is that these maps can be nonlinear, and thus capture non-Gaussianity.